Thanks for joining us all today. For those of you who don't know me, my name is Lucy Tomasini. I am a project manager with the Grower Group Alliance, as well as the Southwest WA Drought Resilience Adoption and Innovation Hub, which is also more commonly or easily known as the Southwest WA Drought Hub. Welcome to the first iteration of our Building Resilient Farming Systems webinar series, where we'll be highlighting 6 of our Drought Hub projects. So the webinar today is brought to you by the Southwest WA Drought Hub, which is led by the Grower Group Alliance. Before we get started, a very quick introduction to the hub, what we do and who we are. So we've been around since 2021 and we're part of 8 hubs nationally, funded through the Australian government's Future Drought Fund. The aim of these hubs is to provide regionally relevant information and support to help farmers and regional communities prepare for and adapt to the impacts of drier and warmer seasons. So we really focus on collaboration in the agricultural ecosystem, bringing together researchers, farmers, grower groups, industry leaders, and so forth to make sure that agricultural research is impactful, accessible, and to really drive innovation. So through funding from the Future Drought Fund, we sought project EOIs from our hub consortium partners that would investigate concepts that contribute to evolving agricultural systems in the Western Australian agriculture. Each of these projects is led by hub consortium partners and delivered in collaboration with growers, grower groups, regional organizations, and industry experts to help ensure that the work is really practical, relevant, and grounded in real-world farming contexts. So the primary focus of these projects is to really generate new knowledge, tools, and approaches. However, over time, some of these innovations may contribute to broader shifts in how agricultural systems operate, and to also build resilience at multiple levels. Today, we'll be deep diving into one of the 6 projects, which is called SPRAYS. It is led by Murdoch University, and it plans to transform broadacre crop production by improving water harvesting into furrows and water retention in regions where water efficiency is low and where there is a drying climate. So today we'll be hearing from Professor Daniel Murphy, who is a biochemist and is also the director of the Bioplastics Innovation Hub at Murdoch University. We'll also be hearing from Cheryl Rimmer, who is a research officer at the same Bioplastics Innovation Hub at Murdoch. So just a few logistics before I hand over to Dan and Cheryl. Please feel free to keep your cameras on or off, but make sure that your microphones are turned off. This session will be recorded and it will be available on our website next week. There will also be a Q&A session at the end of Dan and Cheryl's presentation. So if you do have any questions, you can either hold on to them and put your hand up at the end to ask them yourselves, or there is a little Q&A tab at the top on the little banner. So you can click on it and write your question in there, and I can either ask it for you or you can ask it yourself at the end. So without further ado, I will hand over to Dan.
Great, thanks very much for that introduction. So as Lucy said, my name's Daniel Murphy. So if you drink alcohol like I do, then Dan Murphy's, you should be able to remember my name. Just quick background on myself for those of you who don't know me. I'm from a teaching family. My father taught in many regional locations, and one of those locations was Brookton, which is where I grew up as a kid and where I got my interest in agriculture. And at Murdoch University, we have a Centre for Sustainable Farming Systems, which I lead. And that's really about trying to help growers. A lot of the work we do is through DPIRD and GRDC in collaboration, but help growers to maximise yield, profit. And this one is particularly looking at water use efficiency. And what we're really trying to do here, and why smart sprays and why bioplastics, we're trying to produce products, so new products that can go into the agricultural sector that don't leave a plastic legacy. And I'm sure most of you have heard and understood and appreciated the fact that a lot of synthetic plastics, so oil-based plastics, fossil fuel-based plastics, as they break down, they leave microplastics, and those microplastics end up in the food chain, in water chains, and so forth. So what we're really after is the bio bit, just means biologically degradable. So we're looking for plastics that break down in the environment, leaving no lasting legacy on land or in water. So completely environmentally safe. Basically, they break down to carbon dioxide and water. Cheryl is the staff member employed on this. So the way we're going to tag team here is I'm going to start and talk a little bit about the science and try to introduce this new idea of smart sprays. And then Cheryl's going to talk about some of the work that's been done with actually engaging with field trials and also with different grower groups. And I guess what we're really interested in is, apart from raising awareness on this project, is also getting feedback from yourselves. So if you think this is a good idea or a bad idea or have questions, we really want to hear from you. There's no point us trying to work on future products that could become commercial and available in the future if it's not really the right approach or if we're missing something. So really happy to have a discussion at the end about all of this. So just a slight technical hitch. You might need to do the slides for me because they're changing on my screen, but I don't believe they're changing on the presentation, even though I have sharing capacity. Can you take over that, Jess? Thanks, Jess. Can you go to the next slide? Thanks very much for that. So as an introduction, we're all aware that we're in a declining rainfall. So the wheat belt of WA has had a decrease in rainfall, and that means really our eastern borders are pushing closer to the coast in terms of our deciles. So our rainfall is declining, and the predictions for the future from the climate modelling is that it will continue to decline. Now, at the same time, what I find really interesting is that we have a water use efficiency of about 56%. So that means that of all the rain that enters the agricultural wheat belt, if we take an average, we convert about 56% of that into water use efficiency into the plant. If you think about that, that means that there's about 44% of that water, that rainfall, that we're actually losing. And as rainfall declines and as rainfall becomes more difficult, harnessing that extra water and harnessing every drop of rain is obviously a priority if we're going to continue to maintain and actually increase our yields as we start to help feed the growing world population. Remembering that Western Australia is a major exporter, so we don't have to think about our very small population in WA or our very small population in Australia. We're an export nation and we're feeding a lot of population overseas, and that means increasing efficiency, increasing productivity, and keeping farmers well and truly supported in terms of R&D in this area. So this project is very focused on how we manage water and how we manage water that comes in contact with the ground, and particularly looking, if we can have the next slide, please, Jess, at looking at how we move or how we encourage water to go from the mounds or the interrows into the furrow where the seed has been planted. And this is particularly important at key times of the year. So as we know, we have a lot of false breaks in the WA wheat belt where we have early rain, there's enough rain for the seeds to start to germinate, but not necessarily those really important follow-up rains. So part of the idea of the smart spray, of that coating that covers the soil in between the rows of the plants, is to really help with seedling establishment and trying to maximise water into the furrows. So give those seeds more water that falls on the land, and also to try to protect that water from evaporation so that once it's entered the soil, we don't lose it. So one way of doing that, and it's used a lot around the world, particularly in places like China, is that picture on the right-hand side, which is showing black plastic. And those black plastics in that picture, that drone photo from above, are showing different rates of breakdown. So these are actually plastics that have a biodegradable component. So people are looking at how you might have plastic films that do break down over time. The reality for WA and for Australia is, for broadacre farming, black plastic is a little bit impractical. We're not really in a system where we can roll out black plastic between lines of canola or wheat or lupins or whatever you're growing across the vast areas of the WA wheat belt. So used very extensively in horticulture for things like strawberries, used extensively in places like China, where they have the labour force at a cheaper rate where they can practically do it. But of course, that black plastic, if it's synthetic, if it's oil-based, that lasts in the environment and has to be collected. And if it's not collected, it ends up in waterways and blowing everywhere. But I think we'd all agree that it's very unlikely that we're going to go out and in between our rows of wheat try to lay black plastic and keep it there and not have it blow away. But the idea is great. The idea of having that bare soil in the middle covered, stopping weeds, which is great, stopping evaporation, which is great, and moving water into the furrows where it can really be used. So what we were trying to do is have a spray version of plastic films. Same concept, blocking the soil, moving water, but having something that is sprayable. And because it's bioplastic, because it breaks down, it's compostable, have that plastic disappear by the end of the season. So I've mentioned the idea of protecting seedlings at the beginning, where we have false breaks and we want to use the smart sprays, these plastic films, spray films, to watershed into the furrows. But also they have a purpose later in the season as we're starting to do grain fill and as the season dries out. Because the other problem and challenge we have is we have haying off, where we basically run out of water during that critical stage of trying to make plant biomass into grain. So the idea there is to really stop evaporation as the rains start to cease later in the season and maintain that water inside the soil where it can be attainable by the roots and not lost as gaseous evaporation, so not lost as water evaporation. So there's two roles for this smart spray. If we can get it work early in the season, water shedding, and later in the season, protecting evaporation. And they're quite different challenges, and I'll explain a little bit about that as we go through the slides. Next slide, thanks, Jess. So here we have in the middle, we have a photo of one of our research colleagues, Samantha, and the blue dye there is just really to help visualize it. So the spray has been put on the surface of those mounds, and it is then, in this case, so just a little watering can in the demonstration for politicians. You can see that the water is being applied to the mound with the idea that it then flows off the mound into the furrow. So we're holding that soil together on the mound. We're protecting it with what in this case is a transparent spray. So you can see that little video on the right where we've cast the same spray into a Petri dish, into a film. And you can see those water droplets that are coming out the tip of a pipette are running off and aren't going through that film. So the only difference here is we've poured that chemistry into a little vial, made a little Petri dish circle so that you can visualize it. But the same thing is occurring on the soil surface. As we spray it out, the bioplastic is sitting on that surface and in essence providing a hydrophobic layer and allowing that water to shed into the furrows. Next slide, please, Jess. So a bit of data here, a little bit of science, because this is all new. This is a novel concept. And we were really, really appreciative of the Drought Hub to really fund this as part of their transformational research, looking at trying to demonstrate future ideas that aren't commercially available now, but really starting to profile and get feedback on, would there be interested in this, and is there really a purpose, a need to pursue this line of research? And I said at the beginning, there's no point really doing research unless there's an applied outcome. So we're really happy to have feedback on it. So if we look at the figure on the left, we have spray film thickness on the bottom. On the left-hand side, closest to the axis where the X and Y axis intercept, that's the thinnest film. And as you go to the right-hand side down, past green, blue into pink, the film thickness increases. So what we're testing here is how thick do the films have to be effective at blocking water from infiltrating into the soil. But the key note is don't worry about the 10 and 100. The key note is we're talking about microns. So for those of you that know about wool, I think wool's, correct me if I'm wrong, but isn't good quality wool about 10 or 12 microns? So we're talking about hair thickness here as a reference to you. So microns are a lot smaller than millimeters. We're not talking about putting out something that's an inch or 2 inches or 3 inches thick. If you go and mulch practically anything on your soil, it will help to stop evaporation, but it's not practical. The cost of transport would just kill the productivity gains that you would get. So we're really trying to work on sprays that could be delivered over a hectare using a couple of 100 litres of water. And it'd be interesting to get your feedback on that. That still equates to quite a lot of water, but the practicality is it's unlikely that you would be able to spray out a thickness for less than a couple of 100 litres per hectare onto your intercropping rows. So water infiltration on the y-axis, that's just saying how much water goes in. The higher that is, the more water that goes in through our film. And another way of interpreting that is the higher that number on the y-axis as we move up, the less effective our film is at doing the job we're trying to get it to do. So you can see in the very, very top left-hand corner, there's a very thin bar. The thicknesses of the bars are just the variance, the variation in the data, so the replication. So that top bar is showing basically no infiltration is stopped. All the water goes into the soil. It has no function. And then it steps down as you go thicker and thicker and thicker and get to that pink bar. By the time we get to that pink bar at 100 microns, we have in essence stopped practically 100% of the water, 95% or more has gone into the furrows where the seedling is and not into the mounds, not been wasted. And you can sort of see that in that figure in the middle where you can see the brown soil. It's the soil from Meriden. And you can see the spray in this lab setup has been sprayed onto the mounds of either side. You've got that sort of dark wet colour. And you can see the lighter dry soil in the middle. That isn't the water, that's just setting it up with the spray that then dries. And you can see in the Petri dish, if you've got really good eyesight, there's some water beading on the surface. So in essence, what we're doing is we're spraying onto the area of soil that the plant is not going to emerge from. And we're basically trying to push all of that extra rainfall from the bare soil areas, the interrows, onto where the crop row is to try to maximize the chance of those roots on that growing seedling to intercept and utilize that water and thus increase water use efficiency. Next slide, please, Jess. So this is now a scientific figure from a scanning electron microscope. So we're now talking incredibly high-powered microscopes that are looking at the soil surface. So if we look at the middle picture where there's some text on it, you'll see a little black area up on the top right hand, sort of at 1, 2 o'clock, that says airspace. So obviously that's a void in the soil between the soil particles where water can enter and air can go. We've got the biopolymer in the middle, which is what we're tracking as the spray. We've got an area where it says biopolymer covered in soil, covering the soil particles, and we've got an area called exposed soil. The point I'm trying to make from this high resolution image of the soil surface is the spray is like a spit when it comes out. It's not that continuous film from the video. It's a spitting cover of the soil, but there's enough of a cover, enough of a spray cover to allow the nature of the chemistry in the film, to allow that hydrophobicity to cause the water to repel. So at that level of coverage, which is about 8–10% of the soil surface, we can effectively watershed rainfall into the furrows. That's no problem at all. The spray does that incredibly well and is incredibly effective at doing that. So helping with early seeding emergence and seedlings going through wet, dry stresses through breaker seasons, the spray technology will work very well. The challenge we're working on at the moment is because we only cover about 8 to 10% of the soil surface, we're not blocking pores, we're not blocking air spaces, they're still there. What that means is the spray technology at the moment is actually pretty ineffective at stopping water loss, so stopping evaporation from the soil. So a water bead, a water droplet, is very large. So a rainfall droplet, very easy to move on a soil surface with the spray, very easy to redirect that rainfall droplet into the furrow. Stopping a gas molecule, so water vapor coming out of the soil, is actually another technical challenge which is far more difficult that we're currently working on. Next slide, please, Jess. And interestingly, some of the feedback we had from growers through the Grower Group Alliance and their interaction with this Drought Hub project was saying, okay, so you now have a delivery where you've got a spray where you're trying to move water, either move water into the furrows or stop water evaporation. But the fact that you're putting a spray on the soil, what else could you do with it? How could you functionalize it or add extra benefits? And one of the particular questions we were asked by the Drought Hub was, could you actually use that spray to deliver herbicides? And if you're going to deliver herbicides into the mounds, the interrows, using the spray as a delivery mechanism, could you actually increase the longevity of the herbicide by stopping UV breakdown? Because one of the ways that herbicides break down is biological. The microorganisms in the soil just literally eat it as a food source and break it down. The other way that it becomes ineffective as a herbicide is UV degradation. So what you can see here is some work that we've done through our collaboration in the UK, a university called Bangor University, which happens to be sitting up in North Wales. Why did we go to Bangor University? They have a machine in their laboratory that we don't have in Australia, which will provide a year's worth of UV light, so a year's worth of UV degradation in a matter of months. So in other words, we can test our formulations, our chemistry, over about an 8-week period and know how much degradation would occur in a field over a year. So it's a fast way for a research group to track UV degradation. So on the left-hand side, if you see where it's got smart sprays and there's a figure there, the bottom of the figure say wavelength, so that's UVC, UVB, UVA. So this is ultraviolet light, so sunlight. And then you can see 1, 2, 3, 4, 5 different traces, different figures across wavelengths. They are just different formulations where we're looking at how effective they are at blocking UV absorbance. So the middle figure has smart sprays where the spray formula itself takes out UVA and blocks UVB and blocks some UVC. I've said the wrong thing there. The smart spray by itself, that middle figure, does not block out UVA, does not block out UVB, does block some UVC, which is why the numbers are higher on the left and then flat line from 300 to 500 nanometers. Now, most of the light that comes in contact with, most of the solar radiation that comes in contact with the soil is in that UVA and UVB spectrum. So that's what we're trying to block out, is UVA and UVB. It's exactly the same as what sunburn creams do. That's what they're blocking. So here we're looking on the right-hand side, the figure, and it says smart spray plus UV absorbance. You can see those 5 different data sets, those 5 different lines are increasing their effectiveness at blocking UVA and blocking UVB. In other words, in protecting whatever we deliver, herbicide, fungicide, chemicals, microbes in the spray from UV damage. So we're really excited about the idea of trying to think about how you functionalize the polymers, the sprays, to have added benefit apart from water shedding. And we'd be really, really keen to get feedback on the sorts of things that people might see as advantageous to be adding and trialing within these films. Jess, next slide, please. So just to finish off with, you can let it play, thanks, I'll talk over the noise on it. So this is a slow-mo here of a little film on a loop, where on the left-hand side, we have some soil and just has some fake little Tonka toys in there to show the dust being blown around. And then on the right-hand side, the same airline is blowing air into the container. but you'll see there's no movement at all. That's where the spray has been applied to the soil. Because one of the other feedbacks we've had from growers, particularly up in some of the northern sectors around Geraldton, is can we actually use these sprays for dust suppression early in the season? Or maybe, for example, after something like a moldboard ploughing or a soil inversion, where you might be turning your topsoil over in those areas for things like ryegrass mitigation for high seed loadings of ryegrass, or if you're trying to get lime to depth, for example, a lot of the work that Department of Ag does up there. But what we were interested in is, could we come in afterwards and in essence stabilise the soil? And of course, this could have applications into the mining sector. So that is another feedback that we received from growers, where we decided to try out the product, the idea of spraying, not to watershed in this case, but in essence to stop soil from moving. Next slide, please, Jess. So really, that's a bit of a rundown from me about some of the research aspects that we're doing. This does come under what we call the translational project. So it's blue sky ideas that could have big impact if it works, but still very much an R&D program, which is why you saw a lot of research. But I'm going to hand over to Cheryl now, because she's been responsible for going out and really doing all the grower engagement with some of the grower groups and really trying to get feedback on what might work in a practical sense. So thanks very much. I'll take questions at the end, but I'll now hop off and hand over to Cheryl.
Okay, here we go. Thanks, Dan. Hard act to follow, as usual. So as Lucy said at the beginning, my name's Cheryl, and I'm the Project Research Officer for the Drought Hub project. The slide that's on the screen now is a good pictorial representation of the project, but I'll go into a bit more detail in the following slides. I just want to acknowledge some people that have helped with the project. So I'd like to start by thanking Lucy and Jessica for having us today and for all of their help with the project. I think we've made a pretty good team. We cannot bring these projects to life without the assistance of the grower groups and the farmers. So I'd like to give a big shout out to Glenys Batchelor of MadFig, Nal Isto at YFig, and Michelle Hanley from SAPWA, who happily hosted our project on their field days and found me some awesome farmers to work with. Thanks to Andrew from Quarry Farm, Jason from Batten Farms, and Ron from Cape Lagoon Farms to agreeing to work with me on this project. And a special thank you to Andrew from Quarry Farm, who is being featured in our upcoming video on smart sprays, which should be released by the end of February. So keep an eye out for it. And I'd also like to acknowledge Living Farm and SEER for assistance with the field trials. So I'm just going to briefly run through some of the key project components. This project had quite a few moving parts, which included lab testing, as Dan described earlier. We also conducted some economic modeling to determine in what geographical locations would potentially benefit the most from the sprays. We used the CSRO adopt model to help generate figures for the prediction of adoption rates and speed of adoption. This model is used for predicting adoption for innovative products for use in the agricultural space. We also conducted field trials at 3 locations, one in Meriden, one near Geraldton at Wandana, and one near Esperance at the grass patch location. These were wheat trials. Geraldton and Meriden had Scepter, and the grass patch had Caliber. One of the most important aspects of this project was the field days and associated talks. This gave us a chance to communicate directly with the farmers and agronomists to determine interest in these new innovative products. We also conducted 2 surveys. The questions were primarily based around the inputs to the adopt model. I will concentrate today only on the field trial in Esperance and the field day in Meriden. So I guess these are just some of the images that were taken at the field trial. The purpose of the field trials, I see, is we're seeing if we can mimic the results of the lab testing, but we're also seeing like what other unforeseen difficulties we might have. Because as you know, going from the lab into the field, it's just not that easy sometimes. So the first picture on the top left is just the trial site. It is after seeding, but before the sprays went down. The next image is a close-up of the rows after spraying. Then the picture after that is just a picture of the wheat in the trial after it had grown. The right-hand image is probably the most important image. This is the polymer on the surface of the mound after 2 months. So you can see it's still there, but it's not a continuous surface. The picture on the bottom left is me holding some of the polymer so I could actually pick it up. There was some soil stuck to it. It was no longer hydrophobic though, so it had lost its hydrophobicity. And then just for sort of comparison purposes, the last photo on the right is a photo showing the hydrophobicity of the soil at Murdoch after a smart spray application. So you can see a pool of water there and was just sitting there. So the smart spray in this perfect situation, if you like, is very hydrophobic. So these pictures relate to the field days in Meriden. So the first picture on the left is some samples of cast versions of the polymer sprays, which were on hand to look at the field days. So these ones have different colors and there are different thicknesses. Around 60 people attended the field days in Meriden. There was a lot of interest. I spoke for about 15 minutes. And after that, I got about 45 minutes of questions. People were so interested in this technology. I will go into that in a little bit more detail on another slide. The next two photographs is where I'd sprayed the smart sprays prior to the demonstration so that I could demonstrate the water rolling off from the mounds into the furrow. Everyone was fairly impressed with that. Worked fabulously. And then the bottom photo on the right, we had the Murdoch media crew on site for the field days and obtained some valuable footage for the short film that we were producing to promote smart sprays. But this film will also highlight how important it is that we continue to search for innovative techniques to combat WA's drying climate. The main challenges with this project related to the safe transport of the Gen 0 smart spray material. So I guess it's important to realize that the product that we put out in the field is really early stages and it was no way like a commercial product. The other challenge was the long travel times between Perth and the trial sites, as you can see by the map. And there was also some health and safety challenges with some of the components in the early version of the spray. Now, going forward, these components are going to be removed. And finally, the high stubble load in SPRAYS required a much heavier coating of the polymer than I guess that would be practicable. So that I guess the important part is the key learnings from the project. As I just said, we discovered that very high stubble loadings are not locations with high stubble loadings are not an ideal candidate for this type of product, especially at this early stage of development. Sandy soils in low rainfall areas with low stubble load are our prime target locations. We need to have a lot more work on formulation chemistry, and we need to be able to maintain the hydrophobicity for longer. Some of the components of the demo spray are not compatible with existing farming equipment. However, that component will be removed going forward. And as I said before, there was a lot of interest from the farmers in the potential of this technology, particularly at Wandana and Meriden. The attendees asked lots of questions and they sounded very interested. And I've got an example of some of the questions. So I had, when would we spray? How long will it last? What happens if there is a large amount of rain at once? How much will it cost? And can it be sprayed with existing equipment? So that's sort of about as much as I wanted to say about the field trials and the field demonstrations. I just want to acknowledge our partners and the funding bodies for this project. Without these relationships and associations and funds, it would be very difficult to continue with this important research. Okay, so the big question, how has this project helped to improve resilience to drought and climate variability in Western Australia? This project was a really huge, big step to accomplish that goal. We have shown that the idea is feasible. We need more product development, but it is feasible. We have researched the barriers to adoption, and we have, with our communication with the farmers, we found that they have displayed a huge amount of interest. So the next steps after this project finish is the development of a commercial version of the Smart Spray, which will be a bio-based spray. And guess what? We have funding through GRDC to work on the next phase. So this GRDC funded project started in February of 2025 and is called Novel Biodegradable Smart Sprays for Broadacre Cropping. And the learning from the Drought Hub trial has informed this next project. I've got to read this. This new project aims to develop novel biodegradable smart sprays for broadacre cropping. It will develop and test 2 new biopolymer products, a soil spray to facilitate water harvesting, and a sticky spray for a foliar leaf application. And that's all I have to say. Thank you very much for your time.
Thank you, Cheryl. Thank you, Dan and Cheryl. That was incredibly insightful. Great to hear about your learnings and your challenges, and can't wait to see where Smart Sprays takes us next. So that leads us into the Q&A session. Before I ask a potential question, does anyone have a question that they would like to ask? You can either pop it into the little Q&A tab at the top if you don't want to ask it yourself, or you can just pop your hand up and ask it. I can see Jenny. Would you like to ask your question, or would you like me to read it out?
I can ask it if you like. Sorry if I missed this. I might have just not heard, but I was wanting to know, like the farmers, how long it does last. Because I was kind of wondering if there was a possibility of it interfering in water accessing subsequent crops, because of course the furrows and mounds won't be in exactly the same place.
Thanks for that. It's a good question. These are completely bio-based products, because part of our ethos in the Bioplastics Hub is to not leave any lasting legacy on land or water. So really we can't do anything that has microplastics in it. So they would be a within season degradation and completely gone. We will provide data once we get to a more commercial platform confirming that. But certainly there wouldn't be anything left next year, Jenny. It would break down to water and carbon dioxide.
Thanks, Daniel.
Thank you, Jenny. Josh, you have a question? Joshua?
Yeah, g'day. I might have missed it at the start. Have you quantified these in terms of the ethanol equivalent, like they do in water repellents stuff? Like,
good question there. So the molarity of ethanol is a drop test for looking at hydrophobicity, and basically what you do is, as that number increases, you get more and more water repellent. So we can generate these up to a molarity of ethanol of 5, which is basically as high as the score goes. The question is whether we need it that high, and whether the economics would be better to have a lower number, if that makes sense. So part of what we're playing around in the new GRDC project is really how effective does it have to be? Because you can build more and more effectiveness into the product, but then it will become more costly. So we're playing around with that at the moment. Does that answer your question?
Yeah. Just follow-up question around have you seen any interaction with the texture on the surface at all, or is it just a bit of noise, really?
Sorry, mate, can you repeat that, please?
Have you had much interaction with the texture of the soils you've used, or is that just noise in terms of the extra hydrophobicity you've got?
So certainly we are okay on sandy based soils. If you were to go to a really, really heavy clay on the East Coast, the surface area of that clay probably would mean that your application rates would have to go up a lot higher. But I think for certainly southern Australian soils, the rates of application we're looking at will be fine for water moving. Yeah, but there certainly will be a textural interference because of just surface area. Teaspoon of sand has a surface area the size of addition. A teaspoon of clay has a surface area the size of a football pitch.
Great, thank you. Dave has a question.
Yeah, good on you, thank you. Look, really exciting stuff. Sorry, I'm from the Department of Ag in Canberra, actually in the Future Drought Fund. I think it's, it's wonderful to see these promising technologies come out. I guess the really hard part is, your next step with the GRDC funding to come up with a commercial version and then answer all the questions that farmers have got about, well, how much is this going to cost? How long will it last? Is it viable? Is this really something we can use? So I think it's fantastic and great that you've got that further funding. I just wonder, presumably you'll be building into that next project some further field studies and things where you get the commercial product and then be able to try that at a bit of scale to demonstrate, its practical value.
Yeah, fantastic question. I might hand over to Cheryl to say where the field trials are going in this year, because she's going to be running that component of this project.
Oh, hi. So we've already got some trials lined up for the GRDC project. So we're going to be going back again to the east of Geraldton, and we're going back to Merredin because we found that the soil type when we did the field trial there was the best soil that we should use for trialing the product initially, and we're in the right rainfall zone to have the maximum benefit.
And I think I'll just add on that, because the points you raised are really important. Our whole program, the way it's set up with GRDC, actually has a stop-go in it, and that stop-go is a midpoint where they will bring in consultants, agronomists, chemists, economists, and actually look at the viability of the product. So I think we're all serious, both the funding body and the university, about this being a pathway to a product, not a scientific play. So I think the points that you raised are the valid questions and the hard questions that we have to answer. And, I'm pretty blunt. If we can't do something that is going to be applied in the field at a rate and a cost that farmers can use, then it's never going to make a commercial platform. And we're after a commercial platform because we want to make a difference with this product.
Fantastic. Yeah, all the best with the next trials.
Thanks very much.
Great. Deborah, you have a question?
Yes, hi, thanks. Yeah, that was a great presentation, and I have some familiarity with the project. I work in the Future Drought Fund, much like Dave, and am the focal point for the Southwest WA hub. And in a previous life, I worked with a fertiliser company in WA. So my question is around, how does the spray have an effect on fertiliser applications and fertiliser use, please?
I'm sitting here wiggling because I like designing fertilisers in my spare time. The spray will be compatible with fertilisers. We're actually quite interested in looking at it as a fertiliser coating, as polyurethane gets banned through places like the EU. So actually whether or not you can use it as a coating for playing around with the release rates, but also looking at foliar applications of micronutrients. So we're doing some work there. So I think Cheryl mentioned that the Drought Hub was very kind through the this project to fund the application on the soil. The GRDC one is expanded a bit to also look at viability of sticky spray. So spit on the plant and what can you hold there and deliver. And one of the things we're looking at is micronutrients. The other one is fungicides, and the other one is frost mitigation. So I think what we're really aware of is the base product of a spray needs to have added benefits to probably make it economically viable, and nutrient efficiency is something that we will look at quite carefully. So I think that's a really valid point, and something that we're quite excited about is how we might help change fertilizer technology.
Great, thank you, Dan. All right, that's probably all we have time for today. Thank you so much for your great questions, and thanks again, Cheryl and Dan, for your presentation. Super interesting, and can't wait to hear more. I think I have control over the presentation, but not sure if you can see my slide. But again, thank you all for coming. We hope you found that interesting. Please feel free to scan the QR code so you can learn more about the project and other projects that we have within the Drought Hub. We are running 5 more of these webinar sessions over the next 5 fortnights. So if you haven't registered already or checked those projects out, please do. And feel free to also register for our Hub newsletter, which you'll find on the website as well. Once again, thank you very much, and we'll hopefully see you at the next one.